Okay, I want to volunteer. Okay, Mitchell, come on up. Okay, so this is not math. This is just okay. So suppose somebody grabs on. So let's see. Put your arm here, and then put your arm here, on top here. Right. So somebody wants to bend your arm, right? Like she's going to push up here, and he's going to push down here. Right? How do you resist? Well, one way of resisting is to really clench up, right, and just go like this, and he bends your. Okay, so bend my arm, right, and just start fighting each other, right? Right? Okay. So another way is to relax. Okay, go. So don't lift it, but bend it, right? Bend. Bend. So keep on bending. Okay. So you focus and you relax. Keep on going. Right? I want one more person. Edward. So add yourself in. So just one from the bottom, one from the top.
To bend it.
5 more. Go. Bend. It's not bending. Why don't you guys bend it? Are you trying? Here. More pressure. Okay, keep on bending. Okay, so you relax, right? Keep on going. Right? But you see that I'm not like clenching up my arm. I'm not clenching up my arm. I'm sort of relaxing my arm and I'm focusing, right? See, this part is actually really soft.
Yeah.
Right? Are you guys trying?
Yeah.
Well done. Okay, so the point is that you got to use your muscles efficiently. Okay, and so how do you do that? By using your mind to engage the structure, but relaxing at the same time, so that you don't engage unnecessary muscles. Okay.
Professor, why don't we have review sessions before the exam?
Because I want to make sure that we get through everything. Yeah, but if you want to come in and yes.
And also practice midterm.
Yeah.
Didn't we have that last time?
You did have it last time.
Maybe maybe we don't have it this time.
Yeah, I was thinking not to get it. As you get bigger, you should.
The training will come off.
It really helped.
Yeah.
Okay. Okay.
We can drop this if you want.
Okay. So, right. So we're talking about tests, right? And the main thing that we're using is the comparison test right now, right? So we have the comparison test, right? And the part that we're really using is that, right, if the modulus is smaller than something and the sum of the larger guys converges, then the sum of the smaller guys is also converges. Right? Okay, and remember that we proved this using the Cauchy criterion, right? Notice that this shows you that if the sum of the absolute values converges, then the sum of the original thing converges. Right? If the sum of the moduli converges, then the sum of the original thing converges. Right? Because you just take your C sub n to be the moduli of A sub n. Right? Just take C sub n as the moduli of A sub n, right? And this says that if the sum of the moduli converges, then the original thing converges. Okay, so so this is right. Okay, so we had just finished the root test, and we're going to do the ratio test. So ratio test. So this series converges if the lim sup of the ratio of successive terms in absolute value is less than 1. Okay. And it diverges if a sub n plus 1 over a sub n is greater than or equal to 1 for some, for all n bigger than some n naught. Okay. So you probably remember the ratio test from Calc 2, right? It said that you take the limit of successive terms, right? The limit of successive terms, and if that thing turned out to be less than 1, then it converged. If it turned out to be greater than 1, then it diverges, right? And if it equals 1, then you don't have any information, right? So this is the sort of more advanced version of it using lim sup, right? If the lim sup, all you need is that if the lim sup of this thing is less than 1, then you have convergence, right? So, it converges if this happens, it diverges if this happens. Yeah, Lara.
We don't need lim sup for the divergence.
Right. In fact, that doesn't work. It doesn't work. So you need this. You need this sort of. It's not so easy. It's not so simple to state in this case. Okay. So yeah. So this is. Yeah. Really, you could do something using the lim inf, but this is better than that. Okay. Okay. So whenever you're dealing with this sort of limit statement, the way you want to think is, what would happen if this were literally true, right? The limit. Okay. So the idea is, you think, what if a sub n plus 1 over a sub n actually equaled some number that was less than 1, right? Right. Right. Well, if that were true, then a sub n plus 1 would equal alpha a sub n, right? For all n, right? But that would mean that every time you go to the next term, you're just multiplying by alpha, right? A sub n plus 2, a sub n plus 2 would be alpha a sub n plus 1, which would be alpha squared a sub n, right? So in other words, if this were true, if this were literally true, then your sequence would basically be a geometric sequence, right? Your sequence would basically be a geometric sequence, and if you've got less than 1, then if you've got a geometric sequence where the ratio is less than 1, then you have convergence. Yeah. Okay.
Is there like a condition where this test might not be applicable? Might never yield? You might not be able to determine.
Well, no, because the lim sup is always going to exist, right? So, I mean, this as long as you can get a lim sup and it's less than 1, then you're good, right? So, I mean, it's true that if you get something, equal to 1, then
I was thinking equal to 1.
yeah, if you get equal to 1, then it's one of those you don't get any information things. Yeah, yeah. Okay, so although we don't have equality, although we don't have this literal equality, right? We do have the lim sup being true. So okay, so you say, well, so let's prove part 1. If the lim sup of this thing is less than 1, then then you know that, so here's 1, right? and you know the lim sup is some number less than 1. Okay, so we can, by the properties of lim sup, we can still make these terms smaller than some number, right? Smaller than some number between alpha and 1, right? So choose beta such that alpha is less than, so let's call this thing alpha, less than beta is less than 1. We know, since this is a lim sup, then there exists an n such that an plus 1 over a sub n, absolute value is less than beta for all n bigger than that n. Right? But that tells you that a sub n plus 1 is less than beta a sub n, right? That a sub n plus 2 is less than beta squared a sub n, etc. Thank you. Okay. And since summation beta to k a sub n, as k goes from 1 to infinity, converges, we know that summation a sub n plus k from 1 to infinity also converges. Okay. Right. So we know that the tail of our sequence converges, right? Right. The sum of the absolute values of these guys converges, right? So the sum of the original guys, the tail converges, right? And if the tail converges, then certainly the whole series converges, right? Because that's the important part.
Professor?
Yes.
So the reason why we're looking at big N is to prove that the tail converges, right?
To prove that the what converges?
The tail converges. So big
Oh, the
N.
tail,
Yeah.
yes.
But how do you come from the step where you say then there exists N to like the step below that? How do we know that's true?
How do we know this
No,
is true?
how do we know the step below that?
The step below. That just follows by multiplying both sides, right? Right. We know that for all n bigger than capital N, this is true,
Yeah.
right? So then just multiply through on both sides and you get this thing. Okay. Yeah.
Is there a reason why we don't use alpha instead of beta?
Because we can't get, the lim sup condition gives us control. We can't get these guys smaller than alpha. We can't make these guys smaller than alpha, right? We can only make them smaller than some number bigger than alpha, right? Do you remember the lim sup, the property of lim sup?
The theorem.
Yeah, that said that whenever you have a lim sup, well, you don't have a, it's not a limit control, right? You can't say that I can get all terms, you can't say like given epsilon, there's a time past which everybody lies between this minus epsilon and this plus epsilon. But you can say that there's a time past which everybody lies below this something plus epsilon. So you have only like a half limit condition. Okay, so because we're talking about the lim sup. Okay. Yeah, so we can't, we can't use alpha. But fortunately alpha is less than 1, and so we choose something between it. we can still keep ourselves away from 1. Right? The main point is that we want to stay away from 1. Right? Well, we can do it. Yeah, Helen.
How do you go from absolute value of a subscript n plus 1 to the absolute value of a subscript n plus 2 is less than beta squared? How do we know that?
Well, that's, if you, this is what we had earlier, this thing, right? This is less than beta times this, but this is less than beta times this. So we end up with a beta squared, alpha sub n.
Oh, okay.
Right, and so on and so forth, right? A sub n plus k is going to be less than beta to the k times times the absolute value of k, a sub n, right? Okay, and here we use the comparison test. We say, well, look, right? We've got, this series, and the terms are smaller than the terms of this series. This one converges. Why does it converge? Because beta is smaller than 1. Right? You've got a geometric series with the ratio smaller than 1. Right? And so this thing converges, which forces our original series to converge. Okay, and then the second part, the proof of the second part. Is that somebody's phone? Is that you? It's okay.
No.
Okay. It's a very old-fashioned ringer. The second proof of the second part. Well, you see that if this is going to be true, then in this case, in that case, a sub n doesn't go to 0. Right. Right. If this is greater than if this ratio is greater than 1 for all n past some point, well then your terms don't go to 0, and so you fail by the nth term test.
Can we also prove this using similar tools that we used in the first part? So showing that if it diverges for beta, oh no, never mind. The lim sup is not there.
Right. Yeah. So we don't have a limit. Yeah. So what would be an easier, a weaker version of this would be it diverges if the lim n of this is greater than 1. Okay. That would be, if you did that, then you could do something along these lines. Yes.
Would it be
Greater than or equal to. Yes. Thank you. Someday I'll make a statement that Daeyoung won't correct. Okay. Okay, everybody okay? Okay, so we have here like the root test and the ratio test stated with this new concept of lim sup. You see that lim sup is actually all you need. You don't need the limit to exist, right? Back in Calc 2, we said, if the limit exists, then, and is bigger than 1, then, such and such thing happens, right? But there was always the problem that the limit might not exist. But the lim sup, on the other hand, always exists. So, this is a more powerful statement. Okay, so one application of this is the so-called power series. Okay, so you know already that a series of the form summation c sub n c to the n goes from 0 to infinity is called a power series. Okay, where the c sub n are all complex numbers, right? And the z's are also complex numbers, but z, you think of it as your complex variable. Right? For example, summation, 1 over n factorial, z to the n as n goes from 0 to infinity. Right, so these are your coefficients, right? And this is your variable, right? Those of you who know what this is, what is this? This actually turns out to be a function. It actually turns out to be the complex, the way you define the exponential function for complex numbers. Okay, you use the power series, but instead of just use the power series that you get from the real case, but you extend it to complex numbers, and this gives you a way of extending this and other functions to the complex plane. Okay. Okay. So now, theorem, let c sub n, z to the n be a power series. And let alpha be the lim sup of the nth root of the modulus of the nth term. Okay, and let R be 1 over A if alpha is finite, and let it be, I'm sorry, if alpha is bigger than 0, and let it be infinity if alpha equals 0. Then this thing, the power series, converges in the ring Z on the disk of radius r, and it diverges if Z, the absolute value of Z is greater than r. Yeah, Lon.
What's like the relationship of this theorem to the root test?
You'll see in 1 second. You'll see in just 1 second, yes.
What if C is R?
Then it's one of those you don't have information. Yeah. Okay. So, right. So what this is saying is that if you have any power series, then there is this number. Okay. There's this number R. So there's going to be some number R that R could be infinite, and you can calculate that R as 1 over this lim sup, right? And that gives you a radius in which your series converges. Okay, so this is the so-called radius of convergence, right? R is called the radius of convergence. Okay, and it says also that if you are outside of this, if you take the closure of this and then you go outside of that closure, then you always diverge. Okay, so that these things, have a very sort of fixed form for where they converge and where they diverge. Right, it's always going to look like some open disk with maybe some part of the boundary. Right, in parts of the boundary it may converge or it may not converge. Okay, but you can't have something. You can't have something like, something like this. That's impossible. Okay. Okay. So. Okay. So what's the proof of this? Just consider the root test, right? So apply the root test to your series, right? And what happens? Well, the root test says that you take the lim sup of the nth root of the nth term, modulus, right? Right? Well, what's that going to be? That's the limb suit of this thing times the absolute value of c. Right? What does the root test say? The root test says, as long as this thing is smaller than 1, then we converge. Right? So as long as this thing is smaller than 1, so root test says, if this thing is smaller than 1, then we converge. Right? But that's the same thing as saying that the absolute value of z has to be less than 1 over this. Right? And if it's bigger than 1, then you diverge. Right? And if it's equal to 1, then you don't know. Right? Okay. And if this thing equaled 0, then where would we converge? If this thing equals 0, all we need is that 0 is equal to less than 1. We converge everywhere, right? And that's why we say that the radius is infinite in that case. Okay. Okay, so if we looked at this guy, so examples. Suppose we find the radius of convergence of this guy. Well, what's it going to be? It's going to be 1, right? Because all the coefficients are 1. Take the nth roots of those guys, it's 1. Right? So the radius is 1. Right? So we know this thing converges on this disk. What about on the boundary? We know it diverges outside here, but what about on the boundary? What do we know? What can we say? Does it converge anywhere on the boundary? Right, so we've got this disk. Right. Of radius 1. Talk to a neighbor for a minute. What's the answer? Does it converge anywhere on the boundary? Anybody want to say? Well, if you're on the boundary, then your term has modulus 1. So you'd be looking at the sum of things, right? You'd be looking at the sum of things, but each of the terms has modulus 1, right? And when you take powers of things of modulus 1, well, it still is going to be a modulus 1, right? So you'd be summing things whose absolute value doesn't go to 0. Right, so it's going to diverge, right? So for this guy, it actually diverges at every point on the ring. So its domain of convergence is just the open disk. What if I were looking at something like this? What if you're looking at something like this? What would be the radius of convergence? Well, you look at the nth root of 1 over n squared as n goes to infinity. That's 1, right, the nth root of that, 1 over 2 to the n as n goes to infinity. Well, that's going to be 1, right? So again, the radius is 1. What about on the boundary? So we know that we have convergence inside here. What about on the boundary? Does it converge anywhere on the boundary?
Is the mod of z still 1?
Yes, on the boundary, yes. The mod of z is still 1, right? So you know that if you took the sizes of these things, it's smaller than or equal to 1 over n squared. Right? What do you know about this? If you're summing 1 over n squared, then that converges, right, by the p-test, right? And so that tells you that this thing would converge by comparison test. Yeah, Max?
How do you know that 1 over n to the 2 over n goes to 1?
So this was one of the sequences that this was actually the example that I skipped, but it's in your text. That n to the 1 over n goes to 1. Okay. Yeah, so you should know from your book, basically. This was the one that involved the second term of the binomial theorem. Okay, so in any case, this guy converges, and so this guy is going to converge. So, right, so this is going to converge, and that forces this to converge also, right? By the comparison test, right? Because the modulus of these terms is smaller than this thing, which converges. Okay, so in this case, the domain of convergence would be the closed disk. Would be the closed disk.
Professor,
Yes.
so when we're looking at the boundary, are we always looking at the absolute value? Like, how do we know that we're looking at the boundary and not inside?
Well, so what this theorem tells you is that there is some radius, right? Whenever you have any power series, you make up some power series, there's going to be some radius. And that radius, inside of that radius, you have convergence, right? And outside of that radius, you have divergence. And then when you're equal to that radius, right? When the modulus equals that radius, then you don't know. Okay. So once you run this test, the only thing that you're uncertain about is the boundary, right? Where the modulus actually equals that radius. Okay. And then you have to, like, it involves some. You have to get your hands dirty. Right here, you've got this machine that does all the work for you. It's like, okay, here up pops the R, and then you get the result, right? But here, it's like, okay, now we have to actually think about it, right, and see what happens. Okay. There was kind of a middle example. Summation z to the n over n. Where the radius again turns out to be 1, and this time the boundary turns out to be kind of tricky. We'll deal with it in a few minutes, but in this case, there's only one point where on the boundary where it diverges, and then everywhere else it converges. Do you know one point on the boundary where this thing diverges? X?
Where's z equals 1?
1 equals 1, right? When you're summing 1 over n, then that's a divergent series, right? But it turns out that everywhere else, so this guy's domain of convergence turns out to look like this, right? It's the inside and this one point. Okay. Yeah, Pam.
I'm still a little unconvinced for the first series, so like
that you were like moving it along, and I mean, I understand if you have an angle that kind of divides 2 pi, that you would have a divergence series, because when you're like summing all around, you get 0 and you get like kind of a circle. But what if like, you know, you never sort of go back to your original point, and then like at the end they all add up to 0? Like
At the end, that's the trouble is with that word, at the end, right? Because it's going to keep on going, right, with a significant perturbation every time you add something on, right? And so every time it's going to be bouncing around, you know, I would say, so what you're saying actually, I think, is that if you took some sort of averages of this, then it should tend towards 0.
No. Like,
But, so, do you believe the nth term test? Right, the nth term test says that if you sum terms and the size of the terms don't go to 0, then your series can't converge. Right, we have the so-called divergence test, right, that if you have some series, a sub n, if a sub n doesn't go to 0, then the series diverges. Right? And that's the point for this one, right? The size of these things is always 1. Right? So the size of these things doesn't go to 0. Yeah. But I understand what you're saying. Helen.
So by the comparison test, the summation of c to the n over n diverges, right? That one diverges.
Well, for what z?
For any, because you know that it's going to be greater than the summation of 1 over n.
If you're
because you know the summation from 1 over n diverges.
You know the summation of 1 over n diverges.
And you know that this one's always going to be greater than or equal to that.
Well, you can't really talk about greater than or equal to because these are complex numbers, right?
So it could be less than.
Well, no, it's just not comparable. You could say let's look at the absolute value of it. Right? You could say let's look at the absolute value of it, right? And you could say, well, this thing, if this thing is bigger than 1, then this thing is bigger than this.
And then it diverges.
That would show you that this thing diverges, but it doesn't necessarily imply that this thing diverges.
Okay, I see.
Yeah, so you actually can't argue along those lines. Yeah. Okay. Okay, other questions? Okay. Okay, so just very slowly. Okay, so now we're going to talk about a bunch of tools to deal with series of the form summation a sub n b sub n. Okay, so you've got, basically a series that's where the sequence is a product of two sequences. Okay. So here is going to be our main tool, which is sort of a partial summation formula. Partial summation formula. So if you have two sequences, a sub n and b sub n, we're going to notate capital A sub -1 as 0. We're going to notate a sub n as summation k from 0 to n of a sub k for n greater than or equal to 0. So it's just the partial sum from k equals 0 to n. And so this is going to seem kind of weird, but I think all lemmas seem a little weird, and then you see how they're used. That's almost the definition of a lemma. It's sort of a useful, but it's a useful tool that it's a tool. Okay, so here it is. That the sum from P to Q of a sub n, b sub n equals summation a sub n, b sub n minus b sub n plus 1 plus a sub q, b sub q minus a sub p minus 1, b sub p. And goes from p to q minus 1. Okay, so I'm sort of sorry to show this to you because what is this? It's what it's just sort of some sort of technical lemma that we're going to use. Okay, it's just a calculation basically. So if you don't like it, that's good. Okay, so let's just spread this thing out. Okay, so let's start with summation a sub n, b sub n from n equals p to q. And we're going to rewrite that as, well, n from p to q of, we're just going to rewrite this a sub n as capital A sub n minus capital A sub n minus 1. That's nothing, right? This is the partial sum up to the nth term, partial sum up to the n minus 1th term. Subtract them, you get the nth term. Okay. Then, again, we're going to do something that's not particularly interesting. We're going to break this up into 2 parts. So, right, just this minus that. So just we distributed the multiplication. Okay, and now something equally interesting. We say, okay, well, let's re-index the second term. We re-index the second term as by shifting the index down 1. Right, which means that we have to shift these guys up 1. Okay. We take off the top term from this first guy. So we say this is going to be the sum from n equals p to q minus 1 of a sub n, b sub n, and we separate off the top terms, so aq and bq, right? And we separate off the bottom term from this guy, so we have subtract a sub n bn plus 1 from n equals p to q minus 1, and we write down the bottom term here. So a sub q, b sub q plus 1. No wait, that should be a p minus 1. Sorry. We took off the bottom term, so it's p minus 1. P minus 1. Thank you. B sub n. Okay, and then we're done, right? That's it. Right, so you just combine these things together, right? And you end up with the thing that you're looking for. So this is just a calculation.
Where did the last term come from?
So I took off the bottom term here. So the bottom term used to be the p minus 1 term,
Okay.
right? I just separated that p minus 1 term off. Okay, so I don't think I have time to prove the theorem that this tool is designed for, but let me just state it, okay, and we'll do it in the next lecture. So it's this. So again, let a sub n be summation a sub k from k equals 0 to n. If the a sub n are bounded, if b sub n is a non-increasing sequence that converges to 0, then summation a sub n b sub n converges. Okay, and we'll prove this next time using this lemma. And this will give us so-called Leibniz's theorem about alternating series.
Is that in the term?
I'm sorry?
No, this week is not going to.
Yeah, so regarding the test on Friday, it's only going to cover material up until last Friday's class.